Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find area of the green shaded triangle? Take a moment to study the figure. Then let us uncover the key geometric ideas that make the solution click. Look at trapezoid ABCD. The right side AD and the left side BC run parallel, and the top leg segment AB joins them. The diagonal BD cuts the trapezoid into a white triangle ABD and the green triangle BCD. The green area is our target. Here is what is actually given. Segment AB is 10, the white triangle ABD has area 100, segment AD equals segment CD, and segment BC is parallel to segment AD. The right angle at A is marked in the figure. Focus on the white triangle ABD sitting in the corner at A. Its two sides from A are the leg segment AB and the right base segment AD. We will use it to pin down the shape before we chase the green area. Because the right angle at A is explicitly marked, segment AB and segment AD are perpendicular legs. Therefore, the white area is 1/2 times segment AB times segment AD. Substitute segment AB equals 10, then 100 equals 5 times segment AD, so segment AD equals 20. This length has now been derived, not assumed. The matching tick marks say segment AD equals segment CD. Since segment AD is 20, hypotenuse segment CD is also 20. The area of any triangle is 1/2 its base times its height. We already have a base, segment BC, so the one missing piece is the height, the straight across distance from the apex D to the base. Let us construct it. Drop a perpendicular from the apex D straight across to the baseline BC and mark the foot where it lands as F. The segment DF is, by construction, the height of the green triangle. Now we need its length. Notice that D sits on the right line AD and F sits on the left line BC, and segment DF is perpendicular to segment BC. So segment DF is exactly the perpendicular distance between the two parallel lines. That is the quantity we will now measure. Because segment BC is parallel to segment AD, the perpendicular distance between them is the same at every point along the lines. So the gap beside the apex, segment DF, equals the gap measured anywhere else, and we can read it off wherever it is easiest. Aha! One auxiliary rectangle transfers both dimensions at once. Opposite sides give segment BF equals segment AD equals 20, while segment DF equals segment AB equals 10. Now look only at right triangle CDF. Its hypotenuse segment CD is 20, while leg segment DF is 10, exactly half the hypotenuse. Aha! A leg equal to half the hypotenuse is the fingerprint of a 30-60-90 triangle. Pythagoras makes the other leg segment, CF, equal to square root of 300, or 10 square root of 3. The green base splits at F. Segment BF is 20, and segment FC is 10 square root of 3. So segment BC is 20 plus 10 square root of 3. Now assemble the area. The green triangle BCD has base segment BC and height 10, so its area is 1/2 the base times that height. We are ready to substitute our numbers. Put segment BC equal to 20 plus 10 square root of 3 and the height equal to 10 into the formula. That gives 1/2 times 20 plus 10 square root of 3 times 10. Combine the 1/2 with the height first. 1/2 times 10 is 5, so the whole expression collapses to 5 times the base. 5 times 20 plus 10 square root of 3. Distribute the 5 across both parts of the base. We get 5 times 20 for the first term and 5 times 10 square root of 3 for the second term. Let us evaluate each. The first term is 5 times 20, which is 100. That is the whole number part of the green area. The second term is 5 times 10 square root of 3, which is 50 square root of 3. That is the irrational part carrying the square root. Add the two terms together. The green area is 100 plus 50 square root of 3. Since one term is rational and the other is not, this is the simplest exact form. As a check, 50 square root of 3 is about 86.6. So the green area is roughly 186.6 square units. That is comfortably larger than the white triangle, exactly as the figure suggests. So the answer is 100 plus 50 square root of 3. That completes the solution. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.